edge to all we know. In the vast expanse of the universe lies a deep mystery that eludes our understanding.
Every HR manager knows how tedious time tracking can be.
A mystery that stirs our imagination and challenges our understanding. It is the question of what lies beyond the universe. As we travel through space, we're faced with the realization that our vision is limited and imprisoned within the confines of our observable universe. What lies beyond these boundaries remains a mystery, a cosmic curtain that envelops the secrets of existence. The very concept of beyond becomes a philosophical problem. How can we comprehend the realm that lies beyond our perception? This is a challenge that pushes the boundaries of human thought, sparking our curiosity and encouraging us to seek answers. Everything we see, from the interior of a room to the most distant galaxies that can only be seen through huge telescopes, everything that can reflect or direct light to us, is the observable universe. Currently, the radius of the visible universe is 46.5 billion light years. However, the age of the universe is only 13.8 billion years. How to explain this discrepancy? Well, it all comes down to the expansion of the universe. As a result of this expansion, the areas from which the light is emitted are moving away from us, and so we observe them at a great distance. These 46.5 billion light years are the boundary of our universe, even if the entire universe is infinite. Modern cosmology does not know what may lie beyond the observed boundary. These cosmological limits or horizons are dictated by life itself. We don't see the night sky completely filled with stars because of the limits set by light. For example, light has a certain maximum distance from which it can reach observers on Earth, as if there were a spherical barrier around us, beyond which there are billions of other distant stars and galaxies. This is called the particle horizon and the event horizon. However, these two concepts differ from each other. While the particle horizon establishes the distance from which light in the past reaches us now, the event horizon is the distance from the present to an observer in the future. But beyond these horizons lies another limit, the Hubble horizon. If space objects are beyond this boundary, it becomes impossible to see them, even after billions of years. They are constantly moving away from us at the speed of light. So because of this, it seems to us that the universe is limited, although in fact, it is just light itself that is limited. You're well aware that the light coming to us from bright cosmic objects doesn't travel at infinite speed. For example, the sun is located 94 million miles from the Earth, in which case light will only take 8 minutes to travel from it. And the star Proxima Centauri is located 4.2 light years away from the Earth, in which case light would also take about 4.2 Earth years. So it turns out that we can only see events that happened a certain amount of time ago in the past. Yes, we can say that we look back in time when we look up to the sky at night. So to update our knowledge about some extremely distant objects, such as the HD1 galaxy, which is located 13.4 billion light years away, we would need to wait the same amount of time, provided there are no obstacles like black holes in the way of light. In particular, if we could examine this galaxy in detail, we would learn how our galaxy was formed in the early stages of the universe. Therefore, light detection is important for studying the evolution of the universe. And it is thanks to this that we were able to develop the Big Bang Theory. The consequences of the Big Bang could not but leave a trace. Such a trace was found by researchers in the 20th century who studied theories of the origin of the universe. Back then, astronomers Penzias and Wilson picked up a strange signal with their radio telescopes coming from everywhere. from singularity to this very moment. Thus, the map of the sky where you can see the temperature fluctuations of relic radiation is a spotted pattern where blue areas are below the average temperature and orange areas are above it. These spots allow scientists to study the evolution of stars and galaxies since density changes, also called seeds of structure formation, have formed the hot and cold spots of the SMR. In addition, the largest spots, covering 1 angular degree in the sky, have become one of the proofs of the flat model of the universe. Smaller spots, in turn, have revealed a wealth of data on the composition and age of the cosmos. Thus, the study of the temperature features of the SMB has become another proof of the existence of dark matter and dark energy. Back in 2003, a group of astronomers led by D.N. Spergel found the amount of dark matter and dark energy exceeds ordinary matter by several times. According to the latest measurements, the amount of dark matter is 26.8%, dark energy is 68.3%. Finally, the CMB also revealed to scientists the approximate rate of expansion of the universe, 42 miles per hour per megaparsec. Thus, the CMB provides modern science with a wide range of information about the early and present universe, and, in particular, helps to understand what the future holds for it. It turns out that both the SMV and the space horizon limit what we can see from Earth. Let's now take a closer look at what space horizons are and whether we can still look beyond them. We've already mentioned that the cosmic particle horizon is an imaginary line that forms a boundary for the visible universe, setting a certain distance from which light launched in the past can travel to the observer. So if other cosmic objects are far from the horizon, we cannot see them now. However, our particle horizon is not static. Over long periods, the light still travels its gigantic path, and we begin to notice more and more objects, albeit with the help of special equipment. However, we will never see what is beyond this horizon. But what if I told you that there are ways around this limitation of our space interest? We can't see stars 100 billion light years away directly, but some properties of our universe provide a workaround. Meet the neutrino, a tiny, ubiquitous fundamental particle whose mass can be close to zero. But it's special not only because of this. The neutrino has almost no interaction with matter. That is, it can safely travel over an enormous distance at almost the speed of light. Since neutrinos are formed as a result of many cosmic phenomena, such as nuclear processes in stars or supernova explosions, they can carry data about one of these processes to Earth despite a distance of hundreds of billions of light years. In addition, they can be transformed into particles with even lower energy during their journey. It's precisely because of the elusiveness of neutrinos that scientists have tried hard to detect them. However, further development of ultra-sensitive detectors will allow better detection of neutrinos, and so in the future, thanks to these small particles, we may learn what it is like beyond the cosmic horizon.
We chose Shopify because for us it was the quickest, easiest, and most seamless method of getting our...
In addition to neutrinos, gravitational waves will help us explore the universe beyond our vision. These waves of time arise from the acceleration of massive objects such as black holes, neutron stars, or the rotation of two stars around each other. As a result of such energy processes, such waves travel in all directions at the speed of light, destroying less massive objects and slightly increasing the distance between them. But when they reach the Earth, they no longer have their previous power and do not pose a threat, although they are just as difficult to see. So these wave remnants tell scientists not only what exactly happened outside the visible universe, but also at what distance. For example, in 2016, scientists from the Massachusetts Institute of Technology recorded the collision of two black holes 1.3 billion light years from Earth using waves. Gravitational waves, like neutrinos, are our guide beyond our limited universe, and the development of technology to capture them is the key to our knowledge of the entire universe. But no matter how rapidly our efforts to learn the secrets of the cosmos develop, we're hampered by one serious factor. We can forget about the direct observation of stars, galaxies, and the invisible cosmos for now because of the light they have emitted. The expansion affects another horizon, the space event horizon. It sets a limit for any emitted signals beyond which none of them will ever reach the recipient. Currently, the radius of this limit is 16 billion light years. So even if a galaxy is in one particle horizon, but beyond the event horizon, we'll never be able to interact with it. The emitted signal, for example, from the Earth right now will become longer and longer until it reaches frequencies that we're not yet able to pick up. And the object that emitted the signal will be moving away from the Earth. Therefore, we will not be able to make ourselves known to possible extraterrestrial life if it's too far away. Furthermore, in the distant future, even the galaxies with which we are able to communicate may become unreachable to us. The expansion is shaping the size of this horizon. Much earlier, it reached about 60 billion light years, but now it is only 16 billion light years. In the future, this distance will become smaller. In this case, we'll remain in our space bubble without the possibility of communication and scientific development. As an additional wall to this bubble will be another horizon, the Hubble horizon. This limit is a theoretical point at a distance of 14.5 billion light years from us, beyond which the speed of space objects exceeds the speed of light. That is, the further the light-emitting object is from the horizon, the faster it moves away from us. For a photon, it looks like a race. Farther it is from the Earth, the farther it moves away from it. And only beyond the Hubble limit will the Earth stop accelerating. However, Hubble's horizon is also expanding, allowing distant light to reach our telescopes over time. Therefore, in the future, we'll be able to see more and more traces of galaxies and stars beyond the limit, but the expansion brings with it not only positive aspects. In the very distant future, the Hubble horizon will collapse. It will begin to shrink and stop around the galaxies of the local group. After that, no light from other cosmic bodies, unlike the light that has already gone beyond, will ever reach our cosmological horizon. We'll be cut off from the entire universe. But that's not all. The event horizon and the Hubble horizon will merge in about 10 billion years, forming a new horizon with a radius of 63 billion light years. And then we will not see any events beyond this new boundary. After tens of billions of years, all light emitted beyond the limit will disappear forever. Despite human curiosity, the universe seems to set limits to preserve its infinite secrets. We're surrounded by spherical horizons that do not allow distant light to reach the Earth, taking away our ability to immerse ourselves in the study of the evolution of our universe. Moreover, in billions of years, these horizons will merge, blocking light from beyond the Earth and completely depriving humanity of hope of expanding its knowledge of the unlimited universe. However, the rapid development of modern technology will allow us to record more and more data about deep space in the future, thanks to neutrinos and gravitational waves. And even later, we'll be able to establish new particle horizons on other planets. Although we cannot get rid of these limitations, we can manage them. It will take many more generations before we can leave our own horizon, but when we do, there will be an absolutely limitless number of other horizons that we'll also cross one day. All that remains is to wait. Since the beginning of our species, we've looked up into the sky and pondered the vastness of the universe. We've counted the stars, charted the constellations, and dreamed of what lies beyond our tiny corner of heaven. But did we ever dare to think about the end? No, not the end of our fleeting human existence, but the end of time itself. What will the last days of the universe look like? What will we see, hear, and feel in those last moments? Will everything go out with a bang, or will something completely unforeseen happen? Throughout history, humanity has thrived on exploring the unknown, pushing the boundaries of our understanding. Today we embark on the deepest journey, a journey to the very end of time. Like grains of sand in an hourglass, each moment brings us closer to the inevitable conclusion of the universe. But how and when will it happen? And what does it mean for us mere mortal beings? Crossing unimaginable scales of space and time, we travel billions, even trillions of years into the future. A journey not of distance, but of time, for the sake of exploring the ultimate fate of the cosmos, a journey to the end of time. Here we are in the Anthropocene, in the age of man, our time, our era. This is an era defined by the colossal influence of our species on this blue-green sphere we call home. We have shaped, manipulated, and forever altered the very fabric of the earth in the blink of an eye. Take the Holocene, an 11,700-year era in which all human civilization was born. It has nurtured us from our earliest days, from humble hunter-gatherers to modern, technologically advanced societies. The comfortable climatic conditions of the Holocene allowed us to flourish, to invent, to build. It gave birth to agriculture, to writing, to the very notion of civilization. Nevertheless, as we rushed forward, the losses on our planet became evident. Our relentless thirst for resources, our relentless expansion, caused the changes that mark the end of the Holocene. Climate patterns are changing. Extreme weather events are becoming the norm. Biodiversity is under threat. The equilibrium that has nourished us for thousands of years is teetering on the brink. Our actions have left an indelible mark on the conditions of the earth and ushered in a new geological epoch, the Anthropocene. This is a chapter of Earth's history written by human hands. As we stand on the threshold of this new era, one question arises. What legacy will we leave to succeeding eras? Our journey brings us closer to the year 2500, revealing the dynamic changes the Earth would face. Earth's magnetic field, our protective shield against solar winds, is undergoing a belated shift. The North and South poles are reversing places, an event last observed 780,000 years ago. This amazing turn is disrupting our technology, forcing us to adapt in ways never before experienced. Let us be transported to the year 4385. We're witnessing the return of an old friend, Comet Hale-Bopp. It is a sight to behold. A bright trail of light illuminating the night sky, a vivid reminder of our place in the universe. Jumping to the year 5000, we're confronted with the grim reality of our past actions. The polar caps have melted, leading to a global sea level rise. Many coastal towns once full of life now lie underwater, relics of days long past. In the year 6000, a colossal asteroid looms on the horizon. Its collision with Earth is inevitable, causing a catastrophic event that will change life as we know it. The year 8000, we're witnessing an extraordinary celestial event. A distant star, having reached the end of its life, explodes in a spectacular supernova. Its glow outshines entire galaxies, a reminder of the ever-changing landscape of the universe. The Earth and its cosmos perpetually in motion reminds us of the impermanence of our journey. As we look at the star-studded canvas of the universe, we reflect on the trials and tribulations that lie ahead on our journey to the end of time. The hands of the clock move forward 1 billion years. Our sun, the source of all life, begins to change dramatically. Its luminosity increases by 10%, scorching the Earth with unquenchable heat. As temperatures rise, photosynthesis ceases by 1.1 billion years. The green carpet that once covered the Earth begins to fade, replaced by barren landscapes devoid of life. The air becomes thin, and the oxygen we need is depleted. The relentless heat is accelerating, and by 1.3 billion years, the Earth's once vast oceans are beginning to evaporate. What was once a blue pearl in the cosmos is gradually becoming a dried up brown. The great seas and oceans turn into mere memories. Our journey brings us to the last chapter of Earth's history in the 7.5 billionth year. The sun, transformed into a red giant, consumes our once lush planet, marking the end of Earth's existence. Our home world, which has nourished us for billions of years, is now returning to the cosmic dust from which it was born. Fast forward to the year 10 billion. After its fiery death, our sun is reborn as a white dwarf, a weak, cooling remnant of its former self. From the raging hell of nuclear fusion, it's now just smoldering embers, a silent spectator to the grand cosmic drama that continues to unfold. By 100 trillion years, there's a deep silence over the cosmos. The stars, beacons of the universe, begin to go out one by one. They leave behind a chilling darkness, a universe in the twilight. By 1 quadrillion years, after the extinction of stars, the temperature in the universe drops. Having originated in the fiery origins of the Big Bang, we sink into cosmic winter, finding the universe gradually slipping into the era of starlight is over. The universe has become a cosmic graveyard. These are the last remnants of the stars that once illuminated the cosmos. They glow with a faint, ghostly light, a chilling reminder of the universe's fiery past.
Κάνε ένα διάλειμμα, κάνε ένα Kit Kat.
Who am I? I'm the one who can be 100 different investors all at once. With eToro, I can be Grace, a global tech investor. Or Max, a German local stock specialist. I can be Jan, a passive dividend hunter. Hey, I can be David. This David. With eToro, you can be inspired by investors worldwide. Their knowledge, their strategies, all out there for the taking. Be the investor you want to be. eToro.
By 10 quadrillion years, these white dwarfs had become the dominant celestial bodies. This is the age of degeneration. It is a ghost universe that echoes memories of galaxies and stars that once shone brightly. The age of extinction is a vivid reminder of the endless cycle of birth and death in the universe. But even in its last gasp, the universe continues to evolve. Gravity, the sculptor of the universe, continues its work. Gravity, never resting, rips stars and planets from their orbits, hurling them into the cosmic void. These gravitational interactions sometimes lead to the birth of new stars, their creation heralded by ultra-bright supernovas, echoes of the past universe. Meanwhile, white dwarfs begin to disappear. Over trillions of years, they cool and shrink. Their light dims until they disappear altogether. Dying white dwarfs are reborn as black dwarfs. A black dwarf is the final evolutionary state of a star. Invisible to the eye, they mark the plunge of the universe into darkness. The era of black dwarfs begins. The universe, once a spectacle of light and color, is now a shadow of itself. The journey to the end of time continues in coldness and darkness. As time goes on, the universe continues its relentless expansion, each region of space stretching and thinning. Space-time itself is stretching. What was once an organized whole now expands endlessly into something like a multitude of distant islands lost in a boundless ocean. But within this void, a silent catastrophe occurs. Protons, the building blocks of matter and life, begin to decay. Protons, the heart of every atom, disintegrate into ghostly neutrinos and photons. Matter as we know it is disintegrating. The universe is slowly erasing the last vestiges of its physical history. All that remains are particles of light and black holes. At this point in the journey, the familiar physical phenomena end, plunging us into a new era of cosmic history. We are in the era of black holes. Even the seemingly eternal black dwarfs have disappeared, giving up their mass to the unrelenting pull of the expanding universe. The last remnants of stars have turned into cosmic dust. Black holes are becoming the main, if not the only, celestial objects dotting the universe. In an era dominated by black holes, the remnants of once living galaxies, supermassive black holes are of particular importance. Born from the deaths of massive stars and the merging of smaller black holes, these celestial titans have grown to incredible sizes, absorbing matter and energy on a scale beyond anything we could have imagined. These cosmic events emit gravitational waves, causing ripples in the fabric of space-time. We can think of them as the last sounds of the universe on the verge of its end, the slow ringing of a bell echoing through vast cosmos. Such outstanding objects of the universe as black holes are not as eternal as one might think at first glance. The famous physicist Stephen Hawking in the late 1970s introduced a concept now known as Hawking radiation, the process by which black holes lose energy and therefore mass over time. This phenomenon is a result of specific properties of quantum Dark matter, which makes up 85% of the matter in the universe, creates gravitational attraction, which makes up acting as a counterbalance to this acceleration. Although dark energy seems to be the dominant force at present, we must consider the possibility of a shift in the balance of forces. There are several theories suggesting that it is likely that more dark matter may emerge as the universe expands, slowly increasing its gravitational influence. If the gravitational influence of dark matter exceeds the force of dark energy, the expansion of the universe could begin to slow down and possibly even reverse. This is comparable to the elastic band effect. The universe stretches more and more before the moment of abrupt contraction arrives. This process is also known as the Great Contraction. Great compression will inevitably cause the universe to collapse on itself.